In this video, I'm going to be going through an AS depth in chemistry paper that was set in 2021. So I'll go through the entire paper. Okay, in the previous video, I went through the entire breadth paper as well. So this is going to be just going through all the answers, showing how to get to these answers. So again, I'm going to skip through the answers that are particularly just recall based and definitions based, because these are things you just have to learn. Not much explanation to be given there. However, I'll run through the entire paper, pointing out, which parts are easy to get wrong, little traps you might fall into. Just to be clear then, so the depth paper is typically, as it's in the name really, depth in chemistry. So we're looking at more detailed questions than in the breadth paper. Okay, questions that, link to each other, in a bit more detail. So biggest difference, of course, is no multiple choice, which some may see as a good thing or a bad thing. So we'll just jump straight into it then. Okay, so 70 marks available. Let's go. So first question then, compound of sulfur. A part 1 then, explain what is meant by ionic bonding. So this is one of those definitions questions that you just have to remember. Okay, this is not something that you can, well, you can be taught it obviously, but it's something you just have to be able to recall in an exam. So just for completeness, okay, an ionic bond, okay, it's an electrostatic attraction between oppositely charged ions. The key words to include here are attraction and ions. Okay, the rest is basically fluff. Okay, so it's an electrostatic attraction between oppositely charged ions. You need the whole thing, but make sure you don't say the word transfer or atoms or connection. Okay, you want to say it's an attraction between ions. Okay, that's the most important thing. So that's the main, those are the two key words to include, but electrostatic attraction between oppositely charged ions. Right, then it says dot and cross diagram show the bonding in K2S show outer electrons only as standard. So first things first then, this is ionic. We've just been told this, so please remember it, because most people now, it sounds silly, but we spend so long at A level looking at covalently bonded structures that we draw the wrong dot and cross diagram. So remember, if it's ionic, okay, we're transferring electrons. So potassium, okay, is going to lose both of its electrons. Well, both. Each potassium will lose one electron, to lose two in total. Okay, so potassium loses the outer shell electron and becomes positively charged, and there are two of them. The sulfur will gain those electrons, so 1, 2, 3, 4, 5, 6 for sulfur, and 2 crosses to make 8, and the sulfur is a 2- charge. Just to be very clear on this, we're at A level now, so you are expected to use different symbols for the electrons. Okay, so you have to use dots and crosses. You can't just put all dots or all crosses. They have to mix and match. You have to have 2 of one and 6 of the other. You must include the correct charges, so positive for potassium, negative for sulfur. Notice how we've drawn the diagram. What we haven't done is done some ridiculous dot and cross covalent bond. Okay, because some people will do this and they'll think that that's correct. Okay, that is absolutely wrong. You couldn't be more wrong. Okay, so ionic bonding, remember the difference. You've got to put in the square brackets and the charge, and you're transferring electrons. Other than that, it's a very, very straightforward 2 marks to start off with. And the next one, of course, gives you a different compound, and it's now SF2, and it's covalent bonding. So now we can do our, our diagram as we would normally do it with the shared pairs of electrons. So almost as I just drew it, really. Okay, sulfur can have 2 lone pairs of electrons, and the fluorines, just remember to put the extra electrons in for fluorine as well. Okay, it's very easily forgotten when you're rushing through a paper. As you'll notice, I don't draw the circles. You don't need to draw the circles. They're not required at A level. It's only if you wish to draw them. I think this is much easier to see what's going on. I think the circles just clutter the drawing a bit, so I don't draw them. But feel free if you wish to draw circles around. If you want to draw circles around each one, then by all means go for it. but it's not essential. So there you go. Shared pairs of electrons, one with each fluorine. Again, nice straightforward 2 marks to kick off. So it's 5 marks really. That's very, very straightforward on the first page. So first little 3-mark question then. So at room temperature, K2S is a solid, SF2 is a gas. Use ideas about structure and bonding to explain the difference. So we've really just gone through. I mean, they've given you the answer really on the previous page because they've told you that SF2 is covalent. And because it's a gas, we can safely assume it's not a giant covalent, it's a simple covalent. Therefore, it is held together by intermolecular forces, IMFs, intermolecular forces. I'm not writing intermolecular forces. Whereas K2S is ionic and is held together by strong ionic bonds between all the ions. So, how to answer this question then? It's actually very straightforward. For 3 marks, it's, all you got to do is really say that, K2S, just saying K2S is a, giant ionic lattice, it gets you 1 mark. So K2S, giant ionic lattice. Okay. Or, strong ionic bonds is also good enough. As long as you talk about the structure, that's the main thing. And then you talk about SF2, simple covalent. Now, of course, when you say simple covalent, okay, a bit of exam technique here, you need to talk about the forces. You can't just say simple covalent, you need to say what forces they are. So, you need to say specifically that they have weak London forces. Okay, they're London forces, or you've got a permanent dipole. They'll accept either. Okay, so weak London forces. I mean, technically it does have both, so that's why they accept both. So remember, every single simple covalent has London forces. In this instance, because SF2 is not symmetrical, it does have a permanent dipole. However, it doesn't matter which one you say because both are weak, so it's irrelevant. Okay, and frankly, you don't know which one is the stronger force. Okay, you don't know. You're not told any information that can tell you if the London force is stronger than the permanent dipole or vice versa. I would imagine the permanent dipole is slightly stronger, but you need to name the intermolecular force or name an intermolecular force. The key part is it doesn't have ionic bonds. It doesn't have bonds between atoms. It has bonds between molecules, so make sure you write that down. So strong ionic bonds in a K2S, simple covalent weak London forces / permanent dipoles in SF2, and these forces are between molecules. Okay, and that's quite important. Okay, because having the forces between the molecules make them weak. So 1 mark for strong ionic bonds, 1 mark for the name of the force, and 1 mark for saying that those forces are between the molecules. You can say, strong ionic bonds between ions if you want to be fully differentiating here, but you don't need that to get the mark. So very, very nice straightforward question here. It's just asking you to basically state that they're ionic and covalent, and the ionic bonds are stronger than weak intermolecular forces, and just naming the forces and saying what they're between. Okay, right, so sulfur-hexafluoride is unreactive, blah, 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 a bit of preamble that's not really essential here. State the shape of and bond angle in SF6. So SF6 is octahedral. This is one of the most common, well, this is almost the go-to guy, the go-to octahedral molecule at AS level. 6 fluorines around the sulfur. Again, it's got 6 bonding pairs of electrons that all repel each other equally. So 6 bonding pairs of electrons repelling equally gives you a bond angle of 90 degrees, and the shape is octahedral. Again, these are things you just have to remember. You need to know what shape corresponds to each number of pairs of electrons. If I know that I've got 6 pairs of electrons, I must have an octahedral structure, just as I know that if I have 4 pairs, it's tetrahedral, and so on. Okay, it is something that you have to just remember. Right, why is it unreactive? Well, there's lots of reasons why. There's loads of reasons you can give here. So you can say it's got no dipole. It doesn't have a dipole overall because it's symmetrical. That's good enough for 1 mark. You can also say that S to F bonds are strong. They're strong covalent bonds, so hard to break. And you can also say that SF6, if you wish, has no lone pairs of electrons, which would, of course, make it easier to react. If it had a lone pair, a lot of atoms will react in mechanisms using lone pairs of electrons. So any one of those 3 answers is enough to get you the mark. Right, going on then, question 2. So that whole question that we've just been through, all on structure and bonding, 11 marks in total. And in reality, it shouldn't really be dropping any at that point. There was nothing too complicated in that question at all. Most of it was GCSE stuff. So again, even though it's a depth paper, it doesn't mean it's that much harder. It just means that the questions tend to link a bit better, through the actual question numbers. Right, alkane, radical substitution. First question, and again, it's just a definition. What is meant by a radical? This is just a species, and you need to use the word species, with an unpaired electron. So this is just, again, definition. You need to know the definition. State the type of bond breaking that occurs in radical substitution. So remember, in your first step of the reaction, you have essentially, if you're adding chlorine breaks to form 2 chlorine radicals with UV light. And the type of bond breaking is where each atom receives 1 electron each. And if they receive the same number of electrons, then it is homolytic fission. Just homolytic is enough, but fission is the actual thing you should say. So homolytic fission. So in the reaction, monosubstitution forms a mixture of organic products. So what are the products? So if you take a look back at our alkane, so monosubstitution, of course, means we've got 1 bromine adding on, and it just has to show the 2 different products you can get. So from this, you've got lots of CH3 groups, 3 CH3 groups, and a lone hydrogen. So if you replace one of the hydrogens with bromine, there's going to be 2 possible outcomes. You can either replace this hydrogen here. Okay, that's one way of doing it. Or you can replace one of the hydrogens on a methyl group. Now, it doesn't matter which methyl group you pick. I'll just circle all 3 because they're all the same. Okay, they're like, if you rotate the molecule, it's the same thing. Okay, it doesn't really matter. Okay, it's tetrahedral. Okay, this is a 3D structure, remember, in real life. And they're all the same distance away from the hydrogen on its own. So replacing any of the hydrogens in the red circles is the same thing. Okay, so there's no difference in doing so. That being said, there are therefore 2 monosubstitute products. Now my advice is draw it exactly as they've drawn it above to minimize the possibility of mistakes. If you start trying to draw everything out in displayed formula, you might get confused. So the first product is where they replace the hydrogen on the end here with a bromine. That's 1. And the second one is where they keep that hydrogen and they replace one of the others. So I'm just going to replace the top one, CH2Br, H3C, CH3. It doesn't matter if you put the bromine on this CH3 or this one down here. Nothing changes. It's the same molecule. Right. Excess bromine, then you get further substitutions. Write equation for the reaction with excess bromine to produce 1,3-dibromo-2-methylpropane. So this is nice and straightforward. Okay, now we don't have to use any particular type of formula here. Okay, we are allowed to use any type of formula, which is good. So let's just stick to what we know. Okay, it's much easier this way. CH3, H, CH3, H3C. Now, we're adding 1,3-dibromo-2-methylpropane. Okay, so what we're going to need is 2 bromine 2s. Now, remember that in radical substitution, if you react 1 let's say 1 bromine, 1 Br2, one of the bromines attaches to the compound and the other one is a waste product. Okay, and it forms HBr. Okay, because remember, let's say for example I'm going to get, let's change my pen color a second, orange. Let's say I'm going to get rid of this hydrogen here. The bromine goes on, but this hydrogen ends up floating away on its own. So the bromine, one bromine ends up here instead, and the other hydrogen goes away and joins up to the other bromine to form HBr. So therefore, if I'm putting 2 bromines onto this compound, I'm going to substitute 2 hydrogens away. Therefore, I'm going to need 2 bromines to get rid of, to add 2 and then get 2 HBRs at the end. So 1,3-dibromo 2-methylpropane. So in terms of what that looks like then, so we've got carbon in the middle here. I'm just going to put the carbon chain on first because it helps to spot it. So longest carbon chain is 1, 2, 3. It doesn't matter which one you count as carbon 1. Any of the end ones can be carbon 1. Let's call this one carbon 1, this one carbon 2, this one carbon 3. Again, the methyl group is on the 2 carbon. And then we just have to put it on. So 1 bromine on this one. So Br. Again, I could just draw the displayed formula for this one just to show you what I mean. 1 Br here, 1 H there, 1 H there. And of course my 3 hydrogens there. And I need 2 HBRs as well, because the 2 hydrogens that I got rid of need to go somewhere, and they'll react with 2 bromines left behind to form 2 HBr. Now, as I've said, the common mistake in this question will be not putting enough bromines in the equation. Okay, that is the important bit. Okay, if you've not put enough bromines in the equation, then you won't make any HBr. So people sometimes just think, oh, I'll add a bromine, I'll put 2 bromines on, and they forget that HBr is formed as a byproduct. So moving on then, big long question coming up now. So now we're into the bulk of the question. So a lot of preamble going on here. So let's see if we can just dissect it a little bit. So the first sentence is meaningless. That's just saying what glutaric acid is. It tells you can represent the formula as this, where the N here is a whole number. And a student carries out a titration to work out the value of N. So essentially what they're doing is trying to find out the missing molar mass, as it were. So they know it's got 2 carboxylic acid groups, but they don't know how many CH2s they've got. So they're clearly going to be trying to work out the molar mass at some point to work out what the number of N's are. So they do a titration. They dissolve. Okay, so this is the number of grams of glutaric acid. Solution is made up to 250, and they're taking 25 centimeters cubed in a conical flask, and they're titrated with 0.24 NaOH. So nice standard titration question. So they give you the indicator. So it says phenolphthalein is colorless in acid and pink in alkali. What is the color change at the end point? So basically this is just asking you to figure out, what are you adding to what. So remember that the important part to answer this question is given up here. So it tells you that the sodium hydroxide is in the burette. So if I draw a very bad burette, this is an awful burette by the way. There you go, that's my burette. My conical flask underneath it. The NaOH is in the burette. And that means that the glutaric acid, I'm just going to write glutaric acid, is in the conical flask. Now, when you have a titration, you add the indicator into the conical flask. So that means that when I put my indicator at the start of the reaction, the indicator is going to be colorless because I'm adding it to acid. So the color change will start colorless. Once all the acid has reacted and I add excess NaOH into the conical flask, it will turn pink for the alkali. So the color change is colorless to pink, not the other way around, because they tell you what's going in the burette. Okay, right. In terms of the titers then, Okay, all you got to do is fill in all the values to work out the titers. This is very, very straightforward. It's basically an exercise in can you take away two numbers from each other successfully, and you have a calculator in the exam, so there are really no excuses for getting this wrong. However, there is a common mistake that I will just mention. Okay, notice how I'm putting 2 decimal places for all my numbers. Okay, we're doing titration now. Titrations are accurate to within 0.05 of a decimal place. Okay, or in terms of an error value. So burettes actually read to 2 decimal places, which means all of your values must be to 2 decimal places. If you don't put it to 2 decimal places, you just put 1 decimal place instead, you lose a mark. Okay, it's as simple as that. However, this is something that realistically you should never get wrong. Now, why do they carry out a trial titration? This is just an estimate. This is just basically what you'd have done in practical work during the year. Okay, so it's just to estimate the titers, just to get a good idea of where the endpoint is before you start doing accurate ones. Okay, because you don't want to spend ages adding dropwise from 0 if the endpoint's not till 18. You'll be there all day. So you just add it really, really quickly until you get to 18. You know, the endpoint's there, so then you know, next time I'll get to about 15, I'll stop, then I'll add a bit at a time and see where it takes me. Now, calculate the mean titer. Again, to calculate the mean titer, just to be aware, just to be clear here, you never, ever use the trial to calculate the mean titer. And from the remaining data, you only use concordant results. That is, results that are within 0.1 of each other. So I'm going to use these two numbers here to calculate the titer. So I need to take the average of those two numbers. I don't need a calculator for this. It's 18.25 centimeters cubed. Right, moving on then. Uncertainty in the burette reading is plus 0.05, as I just mentioned. Calculate the percentage uncertainty. So the percentage uncertainty is, remember, it's for titration 1 and it's the titer. So again, before I go into how to work this out, big important information there. You're working out the uncertainty in the titer for the first titration. That is not the trial. That is the first titration. Okay, just be clear on that. Now, percentage uncertainty is the error, okay, multiplied by the number of measurements divided by the actual measurement. So let's just fill this in then. So the error is 0.05. I'm multiplying it. Now, how many measurements do I need for a titer? So back at the table for titration 1, in order to work out a titer, I need 1 measurement for the final reading, 1 measurement for the initial reading. Therefore, there are 2 measurements. Okay, not just the 1. And the actual measurement is the titer itself, which is 18.05. Put that in the calculator. Remember, that will give you a decimal. You need to times it by 100 to get a percentage. Make sure you do times by 100. If you don't, then you will lose the mark because you're not giving the percentage, you're giving the decimal, which is not the same thing. If you do all that, you should get 0.55. Okay, if you know the equation, it's a nice straightforward value. Right, big mark then, 5 marker now. Calculate the value of n in the acid. Give your answer to the nearest whole number. So let's go back up to everything we highlighted then, just to remind ourselves. So we've dissolved the mass of glutaric acid. That isn't really important for the time being. It's in 250 of volumetric. They've taken 25 of that and added sodium hydroxide. And we know from our table what the mean titer is because we've just done it here. The mean titer is 18.25. So therefore, it took 18.25 of sodium hydroxide to carry out the titration. So that's our starting point. So as I said, you know, always work out a number of moles from a quantity you are given. Okay, so actually I'll put number of moles, I'll let me answer a bit better. Number of moles of NaOH, that's the numbers we've got. Because we've got the concentration, 0.240. That's the concentration, and the volume was 18.25. And we need to divide that by 1,000 to convert to decimeters cubed. So again, N equals CV. I'll just put the equation here. N equals CV. Number of moles of sodium hydroxide. You're given the concentration. We know what the volume is because it's the mean titer. And that gives us an answer of 4.38 times 10 to the minus 3. Now, that's the amount of sodium hydroxide. We need to work out the number of moles of acid. I'm just going to put moles of acid. So let's go back up to our equation because there's some stoichiometry here. Okay, 2 moles of sodium hydroxide react with 1 mole of the acid. Therefore, I've got twice as much alkali as I've got acid. So to work out the moles of the acid from the moles of the alkali, I need to take my 4.38 times 10 to the minus 3 and divide by 2, and that will give us 2.19 times 10 to the minus 3. Now, specifically, that is the amount of acid in the conical flask, and if we just go back up again, apologies for the constant scrolling, that is 25 centimeters cubed. So that's the amount of acid in 25 centimeters cubed. Now just remember, we started with 250 and we took 25 out of it. So this is the amount of acid in 25 centimeters cubed. We need to know the amount of acid in 250. So moles of acid in 250 centimeters cubed is simply 2.19 times 10 to the minus 3 times 10 lots of 25, and we get 2.19 times 10 to the minus 2. Perfect. That is the amount of moles of acid in 250. Now we need to work out the molar mass. Now remember I said earlier, we need to know the molar mass because we want to try and find out what the missing value is for that CH2. Okay, so we need to know how much the molecule is in total. So to work out the molar mass then, molar mass of the total is mass over moles. We've got the moles, 2.19 times 10 to the minus 2, that which is easy. The mass is another highlighted value in the question, 2.891. So we take 2.891, divide by 2.19 times 10 to the minus 2, and we get exactly, or pretty much exactly, 132 grams per mole, which is our unit. So from here then you might ask, well, the mass of the total, let's go back up to the top now. So mass of the total is 132. We want to work out what this N is. So to do that, we need to do a bit of quick maths. Okay, what we're going to do is take the known amount. So anything that isn't a CH2, we're going to remove from the number. So this COH and this COOH is nothing to do with the CH2s, and they are 45 each in terms of molar mass. So we just take away 90, okay, from our answer, and we get 42. And that means that our CH2s have a mass of 42. Now, the way to find out how many there are is, well, how much does one CH2 weigh? One CH2 is 14, and therefore the NCH2 is going to be 42, which is the total, over 14, which is exactly 3. And that is your final answer. Okay, if you do get a small decimal because of rounding errors or something, remember the question does clearly say give your answer to a whole number. So give your answer as 3 and you get the mark. So again, all this stuff I've wrote here, okay, I would also put on the answer line down below. But of course, it's much easier for me to demonstrate what I'm doing if I write it up here. So make sure it goes on the answer line underneath your working out, and you get 5 very straightforward, dare I say, marks for just working out a molar mass from a titration, and just, the final bit's quite straightforward. Subtract off the bits you don't need, and then work out what's remaining. So nice and straightforward. A lot of writing. I think the writing is what throws people off, but realistically, I only had to highlight what 1, 2, 3, 4 numbers that I needed, and then the equations given. So a lot of information. Don't be afraid to highlight. Again, don't be too liberal with the highlighting. Don't highlight absolutely every word going, but pick out the really important bits. And again, if you've used the value, tick it off. I've used that. I've done 25, done 250. I've used the mass to work out the molar mass. That's where the marking points are all the way through. So, you know, don't be afraid to come up with your own little systems to make this work. Right. Moving on then. So, big question. And we're still going because there's an extra part to this question that we haven't done yet. And that is, and it's always a common question. It's always a common question on practical skills. So they've used a 25 centimeter cube pipette to measure out the glutaric acid. And before they used it, they washed the pipette out with water instead of the glutaric acid. And they want to know what the effect would be on the titration results. So imagine I've got a pipette. So remember, a pipette is one of those long tubes that you use to suck up 25 centimeters cubed. If I wash it out with water, okay, I'm not going to get it dry completely because as you know from practical work, you never get it dry immediately. You know, if you wait a long time, it'll get dry, but in the pursuit of practical, once you've rinsed it out, there'll be a bit of residual water in there. And therefore, when you suck up another 25 mil, okay, there'll be some excess water in the pipette. If you've got excess water, then the amount of acid will no longer be 25. It will now be less than 25. Now, if there's less than 25 of acid, it means you've got less moles of acid, okay? And if I've got less moles of acid, then I'm going to need less sodium hydroxide. So therefore, the effect is going to be the titer for this experiment will be less or be lower. The titer will be lower because the acid will be more diluted. So fewer moles, okay? They'll be more diluted because the excess water will take up some of the space in the pipette. So when you measure out 25, you'll think you've got 25 of acid, but actually you've got 24 of acid and 1 of water. That means only 24 of the acid are going to react. That will happen quicker and the titer will be lower. So because the acid is more diluted, the concentration is lower, which slash conc is lower, you're going to get a lower titer. So these questions always pop up on practical skills asking what the effect would be if I did this, that, or the other. Think it through. Okay, ask yourself, you know, the only thing that would affect the titer are the number of moles of either what's in the burette or the number of moles of what's in the conical flask. So you need to ask yourself the question, how are the number of moles being affected by what I'm doing? By adding excess water and not washing out the pipette properly and leaving water behind, you're lowering the amount of moles of acid being transferred, and therefore the titer lowers as a result. So, on to question 4 then. Okay, so this is an investigation to find the enthalpy change of decomposition of magnesium carbonate. So this is a big 6-mark question. It's fairly straightforward in the fact that they give you the Hess cycle. Because it's an unfamiliar Hess cycle, they give you the 3 reactions that are carrying out. And they give you the Hess cycle with the arrows for you. So it's actually quite straightforward in terms of a Hess cycle. You haven't got to draw it yourself. They put the arrows in the right position for you. So let's see what they want us to do. So they don't know reaction 1. So reaction 1 cannot be found directly. And in order to work out reaction 1, they're going to do reaction 2 and 3 and figure out what reaction 1 is using Hess's law. So to work out the delta H for reaction 2, they've taken a polystyrene cup, they've added 100 of hydrochloric acid, and they've added 4.215 grams of magnesium carbonate, and there, and then you've got the final solution. They've weighed it all out, they've weighed everything, and they've got some results. For reaction 3, they've actually done it for you, and they've already worked out that the delta H is minus 136.1. So that's actually already done for us. So if we go back, delta H3 on our Hess cycle, we'll come back to this later, we know already this is minus 136.1. So that's helpful. We only need to work out delta H2. And the question, of course, is use the results to calculate delta H for reaction 2 and determine the enthalpy change for delta H1. So assume the heat capacity of the reaction is the same as water, so that's 4.18. So that'll always be the case, by the way. They won't give you different heat capacities. That's a bit unfair. So let's go up then. How are we going to work out delta H for reaction 2? Well, dead giveaway for this is that they've given us these two numbers. They've given us a starting temperature and a final temperature. So we're going to be using Q equals MC delta T. Okay, we can work out a temperature change here. Now, do we know what the mass is? Yes, we do, because we're given the mass as well. We're given the mass of the polystyrene cup and the final solution and the mass of the polystyrene cup. So if we subtract the two values, if we do 124.425 minus 21.415, we'll get the mass of the solution, which is what we want. And if we do that, we get 103.1. So mass is 103.1. So let's plug this into Q equals MC delta T. Again, I'm doing it up here so we can see all the numbers. There are lots of answer lines to do this on. Okay, in a real exam paper, you'd have all this in front of you on a 2-page spread. I don't have that luxury. So Q equals 103.1 multiplied by C, which is 4.18, multiplied by delta T, which is exactly 5. I can do that in my head. And that gives us roughly 2,152.909 joules, and therefore it is 2.153. I'll just round it. Okay, don't round it in the real thing, but roughly 2.153 kilojoules. Okay, in fact, you know what? Let's not get into bad habits just because I'm being lazy. Okay, don't get into bad habits like me. Okay, put the whole number out, or keep it in your calculator, 2.152909 kilojoules. Okay, just to avoid all confusion. Now, in order to work out delta H, if you recall from this, we need to do Q divided by the number of moles of magnesium carbonate. So we are told in the question that we have 4.215 grams of magnesium carbonate. So moles of magnesium carbonate, mass over molar mass, 4.215, divided by the MR of magnesium carbonate, which is 84.3, and that gives us 0.05 moles. Okay, nice round number, and therefore delta H is simply our value, 2.15, that's 2909 over 0.05, and we get 43.06. Okay, positive number, 43.06. We've gone up. We've gone from 20.4 to 20.4 to 25.4. We've increased temperature, therefore it is an exothermic reaction, therefore our delta H is minus 43.06. Now we can go back up. Minus 43.06 is on this arrow, 136.1 on the other arrow. So I'm going to go down this arrow, so I'm going to keep the sign the same, so minus 43.06. I want to go back up this arrow, so I've gone down here, followed the arrow, kept minus 43.06. I want to go up this arrow, so I have to flip the sign. If going down is minus 136.1, then going up is plus 136.1. So I add 136.1 and I get plus 93.04. And that is the correct answer. And if you do all that working out and you get the correct answers, you get 6 marks on the spot. Okay, so just to be completely clear, it's plus 93.04. All of these marks are obtained by just pure mathematics. Okay, if you can confidently use Q equals mc delta T to work out an enthalpy change, plug it into a given Hess cycle, you're not going to work this out yourself, it tells you what it is for you, and then just put the numbers on the lines. No multiplications necessary because they're all 1 moles of everything. Add them together and you get 93.04 and 6 very, very easy marks, even though the question looks difficult. On the face of it, you probably look at this and go, oh my God, what do they want me to do? In reality, all they're asking you to do is a simple Q equals mc delta T calculation, followed by a very straightforward Hess cycle. So again, 6 marks, they're just giving them away at this point, I think. So moving on then, look at all that space you can write that in. That does not take that much room. Like, I wrote it in barely a couple of lines. But yeah, again, don't have to fill the space if you don't need to. It really isn't necessary. Right, moving on then. Methanol, okay, manufactured by carbon monoxide and hydrogen. They give you the equation, they give you delta H, and they want you to tell them the equilibrium constant for the reaction. So the equilibrium constant, of course, Kc. Okay, when you write the expression, just include the actual letters. Okay, so it says if it says write an expression, don't put the numbers in. Okay, even though the numbers are further down, don't put the numbers in. Okay, just put the square brackets and the actual species. So first things first then, it's products over reactants, remember, for this. So it's a concentration of CH3OH. Square brackets, by the way, are essential. You cannot ignore them. The square brackets indicate concentration. Curved brackets will lose you the mark. And if you think I'm being pedantic, check a mark scheme. It tells you do not allow curved brackets. Right, concentration of carbon monoxide and the concentration of H2. And of course, in the equation, there are 2 moles of H2. So this is a squared number. And that gets you a mark. So mix them together, gives you equilibrium concentrations of carbon monoxide and H2. They tell you what the value of Kc is, and they want you to work out the equilibrium concentration of CH3OH. So all this now is doing, for 2 marks, plug your numbers in. 15.4, okay, is Kc. That equals the concentration of CH3OH, which is unknown. Divide that by 0.57, which is carbon monoxide, multiplied 0.4 squared for hydrogen. Bit of rearrangement now. Okay, a little bit of rearrangement. So to work out CH3OH, we simply have to take both of these numbers, shift them up to the other side. So now we have 15.4 multiplied by 0.57 multiplied by 0.4 squared equals my CH3OH. Shove it in the calculator nice and quickly, and you get 1.40448. It does not tell you how many significant figures to use, so just put the whole answer on the answer line and you get it correct. Very, very straightforward. Right, moving on now. What does the numerical value tell you about the position of equilibrium? So what that means is if Kc is 15.4, where is the position of equilibrium? So very, very straightforward answer to this. Remember from your Kc stuff, you've got to remember this. If Kc is 1, then the position of equilibrium is in the center. If it's less than 1, it's on a reactant favored, and if it's bigger than 1, it's product favored. So a value of 15.4 means the position of equilibrium is to the right. And if you write those words to the right, you get a mark straight away. Moving on then. So looking at catalysts then. New method of making methanol using a nickel gallium catalyst. Methanol can be produced at a lower temperature than the old method. 2 reasons why it's beneficial for the environment. You find these questions very, very often. It's always the same answers pretty much. So why is lower temperatures beneficial? So less fossil fuels used. That's an easy one. and less CO2 emissions. You would think that these are two of this is the same answer, but it's actually not. Okay, so less fossil fuels and less CO2 emissions are two different answers, and they are the only two answers that they accept. I mean, if you don't put less fossil fuel use, if you write less energy used instead, that's fine, but it's fossil fuels. So less fossil fuels or energy used and less CO2 emissions are your main things. So part D then, nickel and gallium in period 4, what block in the table does nickel belong to? If you get this wrong, you should probably drop A-level chemistry altogether, because all it requires you to do is find nickel or gallium on the periodic table and figure out which block they're in. And if you remember what the names of the blocks are, S, P, D, or F, it's a D block. Okay, I'm not going to even dwell on this. It's a D block. Right. Electron configuration of gallium looks difficult on the face of it, but actually it's not. Okay, because it looks really complicated because gallium's so far down. But all the electron shells are full apart from its outer shell. So as long as you remember what the order is, it doesn't really matter. So let's just write it down then. So 1s2, okay, then we've got 2s2, okay, 2p6, okay, 3s2, 3p6. Now at this point, now I'm going to do it differently because I'm, I do it properly. So in terms of how the electron orbitals fill up, the 4s2 will fill up before the 3d10 fills up. Okay, in second year in transition metal chemistry, this becomes very important. But notice these are all full. If you can remember what the shells are consisting of, so if you know the first shell contains an s orbital, the second shell contains an s and a p, and the third shell contains an s, a p, and a d, as long as you put them in roughly the right order, it's fine. Okay, if you do put the 3d before the 4s, it's fine. They'll accept the answer anyway. Doesn't matter. And then the final one is just 4p1. Okay, because gallium is in the p block. It's got one electron in the p block, and that's all you need to write. So it looks complicated, but it's actually very, very straightforward. Okay, the 4s to the 3d10, if you put it the other way around, it doesn't matter. Okay, the exam board will not dock your mark for it. However, I'm doing it properly, and the 4s comes before the 3d. That much is how it should be done. If you swap them around, it doesn't matter. Right, element A is in period 3 of the periodic table, and it gives you the first 6 ionization energies of element A. Explain your answer of what is element A and why. So, whenever we use ionization energies, we're looking for what we call a big jump. So we're looking for the point at which the numbers rocket. So 789, 1577, that's not big. 3232, not that big. 4356, not that big. 16,000, there's a big jump. Okay, so there's a big jump between the 4th and the 5th. So that means there is a change in shell. Now, if there is a change in shell, that means that the first 4 electrons have been taken out of the same shell. So that means you've got 4 electrons on the shell, on the outer shell, I should say. Okay, so 4 electrons are on the shell. So therefore, it's probably in group 4 because it's in period 3 of the periodic table. So this is a really important point here. It's in period 3, so that's not transition elements. Okay, period 3 doesn't have transition elements. So if you've got 4 electrons on the outer shell, then you're in group 4. And therefore, it is the element in group 4 in period 3 of the periodic table. So the answer is silicon. And the explanation is that there's a large increase between the 4th and the 5th ionization energies. IEs, there you go. Large increase between the 4th and 5th ionization energies. There you go, nice and straightforward. But again, looks complicated, but when you find the big jump, it's actually quite straightforward. So, moving on then to question 6. Okay, so they're investigating the rate of reaction between strontium and water. They've measured the volume of gas every 10 seconds. They've plotted the graph of volume against time. So this is something I can't really do, but draw a best fit curve on the figure and determine the rate of reaction at 50 seconds. So to do this, okay, show you working on the graph. So let's see if I can get it so I've got the whole curve in. Close, that'll do. So line of best fit, this is where my line of best fit goes very bad. So it's one smooth line of best fit. This is going to be awful, by the way. I'm just going to freehand it. Again, yours will be better than mine. I can't really do it on a graphics tablet. There you go, there's a line. And then it says to work out the rate of reaction at 50 seconds. So you find 50 seconds on your graph, which is here. Once you've found, that's a terrible line. Once you've found 50 seconds, you need to draw a straight line tangent that just about touches the curve at 50. Mine does not, but you get the idea. Straight line tangent at 50. Okay, work out the gradient. Okay, y over x. Okay, again, you need to do yours properly. I haven't. So tangent at 50 seconds, gradient y over x, and that is your rate of reaction. You should get, in terms of what your gradient should be, okay, it should be about 0.44. Okay, they accept any answer within 0.2 of that. So that means any answer between 0.24 to 0.64 is correct. Okay, but I can't really go through that. I can't really go through this question that well, but it's just basically plot this graph. Well, draw a best fit, draw a tangent at 50, y over x, work it out, put the answer down, and you get 3 marks. Nice and easy. Okay, so second student is going to use a different method, and instead they're going to use to measure the loss in mass over time. So they put it on do decimal point balance, recorded the mass every 10 seconds. 2 different things to do then. So you're going to do advantage and a disadvantage. So the first advantage is that you're not going to have any loss of gas. Okay, so there's no loss of gas. So obviously if you're doing a gas syringe, there's a chance that when you start the reaction and you're in that split second when you throw the chemicals in and you put the bung on, some gas will escape. So by doing mass instead of gas, you don't have to worry about any loss of gas, and you can measure the mass loss accurately without worrying about random fluctuations. The disadvantage, if you look at the start, they're only using 0.26 grams of strontium. That's a very small number. So again, 0.26. So the disadvantage of this is you're only going to have a small loss in mass. That's going to be hard to plot. So, you've only got 0.26 to start with, and the only thing you're losing is the mass of the gas, and the gas doesn't weigh a lot because it's hydrogen. So not only do you start with a very small amount of strontium, but you're producing hydrogen, and that's the only thing that's going to escape. This is a very light gas. This is the lightest gas there is. All this strontium hydroxide will stay behind and will be part of the mass still. So your loss of mass is going to be very, very small and possibly hard to measure accurately, especially if it's only a 2 decimal point balance. Okay. Third one then, a third student repeats the experiment using the same amount in moles of barium as strontium. Calculate the mass of barium the student uses. So essentially, to work out the number of moles of barium, you need to work out the moles of strontium first. So the moles of the strontium is 0.26, which is what they started with, divided by 87.6 molar mass. That gives you, roughly 2.9 blah, 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 times 10 to the minus 3. That is equal to the moles of barium, because it's just told you that. And therefore, the mass of barium is the number of moles. So 2.9 times 10 to the minus 3. Okay, obviously there's extra numbers there. 2.9 something, something, something. Multiplied by 137.3. And you should get 0.41. And because they're asking you for 2 decimal places, ignore the rest of the numbers. The answer is 0.41. So you work out the moles of strontium. That's the same as the moles of barium, times by the molar mass of barium. and you get the mass of barium. Nice and straightforward. So, student observes the rate of reaction with barium is different to the rate of reaction with strontium. Describe and explain the difference. So 6 marks here for this, and huge way to get marks here. So on the figure 1, sketch the graph for barium. Now barium is further down the group. Okay, it's further down group 2. So it's going to be more reactive. So more reactive means that my line will be steep. In fact, I'll do it in a different color. It means my line will be steeper initially. However, they're using the same number of moles, so it will level off at the same amount of gas. Okay, so it starts off steeper, levels off earlier, and at the same amount of hydrogen as for strontium, because that's the limiting reagent. Okay, the amount of hydrogen should be the same, but the graph is just steeper. Now, in terms of explaining this for 4 marks, this is a massively easy question for 4 marks. So, first thing you write, it sounds like a really ridiculous thing to write, but you just say describe and explain. So describing first. So just write barium more reactive than strontium. That's 1 mark. Okay, stating the obvious gets you 1 mark. Then we have to talk about the rest of it. Okay, so why is it more reactive? So barium, I'm just going to do this in terms of barium. You can do it in terms of strontium, but I'm going to do it for barium. So barium has a greater atomic radius. Now you could obviously write that strontium has a smaller atomic radius. That will also get you the mark, it doesn't matter. So barium has a greater atomic radius, a 2nd mark. Therefore, you've got, more shielding. And therefore less nuclear attraction. Okay, and the shielding outweighs the nuclear attraction, so you can say shielding outweighs nuclear attraction, so shielding outweighs attraction. That's your 3rd mark, that's all that's 3rd. So more shielding, less nuclear attraction, or shielding outweighs the attraction for the 3rd mark, and therefore it is easier to remove electrons in barium. And that's it for 4 marks. Easy to remove E- in barium. 4 marks. And for that, and for the sketch, for 6 marks is an absolute gimme, because this is just very straightforward, describing trends, nothing too complicated about this. So but again, keep your points straightforward. Okay, don't go writing essays, bullet point them. Okay, barium's more reactive, barium has a greater atomic radius, more shielding, less nuclear attraction, and the electrons are easier to remove. That's all you need to say. Okay, again, brevity is key here. Okay, make your points and move on. So I will do that now. So next one then, we've got 2-chloro, 2-methyl propane, organic liquid. They're preparing it by reacting methyl propane 1O with concentrated HCl. Write a balanced equation for the reaction. It's once you use skeletal formula, which could be an issue, but again, be careful with skeletal formula. So they're reacting 2-methyl propane 2ol. So we need to draw 2-methyl propane 2ol. So let's draw propane first. So 1, 2, 3. Okay. And now we need to put on a methyl group at the 2 position and an alcohol group at the 2 position as well. So that's what 2-methyl propane 2ol looks like. We're adding HCl. That doesn't have to be skeletal. And we're making 2-chloro 2-methyl propane. So again, just do it as a 1, 2, 3. That's propane, 2-methyl, 2-chloro. And, okay, we are making something else because the OH has got to go somewhere, and this H has got to go somewhere, so we also make H2O. So again, 2 marks for this. It's not very difficult. Okay, in terms of skeletal formula, if you want a good method to do it, draw the longest carbon chain first and then add everything else on, and that way you can't go wrong. Okay, so you need the skeletal formula and the correct balanced equation. Again, there's no balancing required, but including the water, I think is the most obvious error that I would see. Okay, part B. Okay, big 6 marker again. Lots of 6 markers on the depth paper. They give you a method, so they're adding 10 centimeters cubed or 7.7 grams and 30 of hydrochloric. Stoppered it. They've shut the flask until they're separated into 2 layers. They give you the densities. These are quite important. We'll get to that later. After purification, the percentage yield is 76%. Explain how you could get a pure dry sample from the mixture in the flask and calculate the mass of pure product that I would expect from the preparation. So let's go through the purification first. Okay, we are purifying a liquid. Okay, therefore don't ever talk about recrystallization. Okay, you can't recrystallize a liquid. It's not a crystal to begin with. Okay, so get that out of your heads immediately. Okay, to purify a liquid, we need to use a separating funnel. So the first thing you know is a separating funnel. Okay, now separating funnel, you haven't got to draw a diagram, but honestly, I don't see the harm in it, frankly, because it shows you know what you're on about. And you'll have 2 layers in your separating funnel. Now, the layers will be different, okay, depending on the densities. Okay, now, the densities, 0.85 grams per centimeter cubed for our product, 1.18 for the HCl. So that means our product is in the top layer because it's lighter, so it's going to be on the top. So CH3 CCl is on top, HCl is on bottom. So the one we want is on the top. That's fine detail. You need to include things like that to get the top marks. So you remove bottom layer. So remove bottom layer. Keep top layer. Now, when you have your top layer separated, you need to do a couple of things to it. Okay, first thing you need to do is add an anhydrous salt. Okay, so add anhydrous salt. And you should, to get full marks, oops, I spelled salt wrong, that's terrible, guys. And to get full marks, you should name the salt. Okay, you need to think of a name of an anhydrous salt. Remember one of them, and you won't need to remember any more. So there's 2 that we use typically. Magnesium sulfate is one, or calcium chloride. Okay, remember one of them and use that all the time. So add your anhydrous salt to remove water. Okay, then if you want, you can filter to remove the salt, obviously. So you can filter to remove the salt, and then the important thing is you redistill the product, and specifically you want to redistill it at the boiling point of the product. And if you look back in the question, right at the beginning, they have told you the boiling point of the product. They haven't done that for no reason. The boiling point is what you want to redistill at, because that's what you're going to collect at. So when you distill, you have to boil the product and collect it. So you're going to redistill the product at 50 degrees Celsius. This is the fine detail. So just saying separating funnel, anhydrous salt and redistill will get you some marks. However, in order to get full marks on these questions, you need what's called fine detail. And the fine detail, I'm going to underline in red. Okay, the fine detail is, this first bit. Okay, saying which product is where, that's the fine detail. Naming the anhydrous salt is fine detail. And knowing the temperature at which you are redistilling is fine detail. Okay, that's what will get you the 6th mark or the 4th mark. Okay, and this is a banded question. You can get either 1 to 2, 3 to 4, 5 to 6. If you want the top of that band, you need fine detail. Okay, so include the fine detail. That's all you need to write, though. In terms of separating funnel and and how you prepare the pure dry sample, that's it. That's literally it. Okay, so again, I think this is the key word here, that they say dry. Dry doesn't mean solid. Okay, dry just means no water. Okay, so that's what the anhydrous salt does. People see the word dry sample and they think recrystallization and want to make crystals and remove all the liquid. That's not what dry means in this context. What it means is you want to have no water in the liquid. Okay, but that's all you need to write. So not a lot. And the second part is working out the amount that you would get. So, okay, let's just work it out then. So we're told we've got, I think somewhere up here, 7.7 grams of our starting material. Okay, now it tells us that the hydrochloric acid is an excess, so we can ignore it. We've got 7.7 grams of our starting material, CH3,3COH. So let's work out the moles of that first. So number of moles, 7.70 over the molar mass of that is 74, and that gives us 0.10405 moles. From here then, we're told that the percentage yield is 76%. Therefore, we need to work out 76% of this number of moles. It's a 1-to-1 ratio, I believe, because we did the equation earlier. It's a 1-to-1 ratio, nothing to worry about there. So we know the number of moles of starting material, and the moles of the product is going to be 76% of what the number of moles we start with. So essentially times that by, so the number of moles of product, so moles product is 0.10405 multiplied by 0.76, which is 76%, and that gives us 0.0791 moles. And then to work out the expected mass, you simply have to take the number of moles, so mass equals N times MR. You take 0.0791 multiplied by the molar mass of our product, which is 92.5, and that gives us 7.315, and that's it. Okay, just bear in mind, in order to get the top marks, in order to get 5 or 6 marks, you must get the correct mass. Okay, just make sure you take into account the percentage yield. Again, in terms of a big 6-mark question, loads of information going on here, but in terms of what they're asking you, it's actually not a lot. So basic run through of the separation funnel and purifying a liquid, and again, this is always the same. It never changes. The purification of a liquid never changes. Okay, and again, mole calculation, very, very basic stuff, nothing too complicated apart from percentage yield. So moving on then. Nearly done actually. Right, so compounds A and B are structural isomers. Compound A is a secondary alcohol. What is the systematic name of compound A? So it tells you in the question here that compounds A and B are structural isomers. So that means you've got, so you've got 1 CH3, 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 OH. You've got to rearrange this to make a secondary alcohol. Well, this is a tertiary alcohol, and to make a secondary alcohol, you just have to rearrange this chain into a different structure. So the only way you can really do this is if, well, think of a secondary alcohol. OH has to go to a carbon that goes to 2 other carbons, so it looks like this. And once you get this far, there's only actually one other thing it can be. It's got to be another carbon there. So therefore, it's got to be butan-2-ol. Okay, put the hydrogens in, and you get butan-2-ol. Compound B is a branched primary alcohol. It's refluxed with potassium dichromate. Write the reaction that takes place. So again, branched primary alcohol. So think about it. Okay, if it's a primary alcohol, it's got to be COH, and it's bonded to carbon. Carbon. If it's branched, then it must be a CH3 here. Okay, otherwise it's not branched. So this is what we're starting with. And it says use structures for the compounds. So it doesn't matter what formulas you use. It just says use structures. So let's just do it like this. If we carry out this equation, then we're refluxing with dichromate. So 1, 2, 3, 4. Let's put this on and this on. Nice and straightforward, this. Not overly complicated. There we go. So nice and branched, and we're going to add O for the oxidizing agent. Now it's a primary alcohol, so it's going to go all the way to a carboxylic acid. So we need 2 of these. And then we're just going to make the carboxylic acid. Nice and straightforward. CH3 here, H there, and CH3 here. And we make 1 mole of water. Okay, because remember, you only get water from the first oxidation. The second oxidation gives no water. And from that, you get all your marks. Okay, 3 marks for that, by the way. 3 marks for getting the correct reactant. But again, a branch primary alcohol, it tells you everything you need to know to work it out. The key part then is getting 2 O's and 1 H2O. The product is very straightforward because it says it's refluxed in the question. So therefore, it must be going to a carboxylic acid. So there it is then. That is the 2021 depth in chemistry paper. So hopefully you can see there's lots of 6 markers in this paper, lots of big longer questions. However, they're all fairly straightforward to answer. Okay, there are lots of words and there's lots of information to pick out, but if you get good at picking out all that information and then using your knowledge to apply it, you'll find that you start collecting marks in these papers very, very quickly. So that was the 2021 depth paper. I'll probably do some other papers at some point, and there'll be videos for those on the channel as well.